This week we have a presentation on deep learning. So some motivation for deep learning. Historically, deep learning neural networks has been first proposed in 1957 by Rosenblatt with the perceptron, which we have seen some weeks ago. So the perceptron is basically a linear model that has been developed with some kind of learning rule that we know is now suboptimal, but still was a new thing in 1957, and was also able to be implemented on electronic devices, so with analogic electronics. So this was a first attempt into developing, I would say, bio-inspired devices, so devices inspired from how we know the brain is working. And in 1967, we have Marvin Minsky from MIT that demonstrated that the perceptron is in fact unable to process non-linearly separable data. So that was a big thing at that time, because it demonstrated that in fact we are dealing with some model that is quite limited, that is working only with linearly separable data. And that demonstration from Minsky in a book named Perceptron generated a big disinterest from the scientific community toward such neural approaches. And so from like the 1970s up to 1985, 86, there was not much things done on that aspect. Grummelhart, Hinton, and Williams demonstrated in 1986 that we can train I would say several layers of perceptron neurons organized in some ways using what they call the gradient backpropagation. So what we see in the previous module on perceptron, multilayer perceptron, was in fact that breakthrough. So the idea that we are able to backpropagate the gradient through many layers of perceptron neurons. And that changes things, that makes it much more interesting. So we are able now to deal with, I would say, non-linearly separable data using such an approach. So there was a lot of developments in terms of artificial neural networks in the late 80s, 1990s. Up to, I would say, 1998, where we've got new approaches that were proposed, basically the SVMs that we saw 2 weeks ago, 2 months ago. So SVMs proposed an approach that was well-founded, mathematically speaking, and was really well performing in practice when it was used properly. And that kind of creates some pushback on the neural networks. Because they were not as, I would say, strong as SVMs. They were not easy to deal with, mathematically speaking. So we don't have, I would say, strong mathematical demonstration that it works well compared to SVMs, where I would say there is a strong theory behind it. And as such, neural networks became more marginal in the community. It was not that much studied in between 1995 and 2010, I would say, 2005. So there was another, I would say, down in the interest of the community toward this. In 2006, there were the first deep neural networks architectures that has been proposed from the labs of Hinton, Lequin, and Lequin proposed some convolutional neural networks before then. But in 2006, we were like looking at new approaches based on ideas that allow to train deep neural networks versus the usual multilayer perceptron that was limited to about 2 hidden layers. More than that was not working well up to that time. And in 2012, there were like important breakthrough in terms of the results on concrete results, practical results. For instance, for object recognition. So the team of University of Toronto proposed convolutional neural networks trained with GPUs that achieved really the best results on the ImageNet challenge. So that was an important breakthrough. And there was also a nice demonstration from Microsoft on speech recognition. So it really shows that deep learning are really capable of disrupting the field. Is that this is really a disruptive technology that can allow to have significant improvements for many applications. So there was following that an explosion of private investment in machine learning, especially in deep learning. So we have companies like Google, Microsoft, Facebook that invested to build teams of researchers in machine learning that recruited a lot from universities, either graduate students that recently got their diploma and even professors. So that investment was also reflected by an increase of the pace of research and the capacity also to develop approaches with, I would say, a good level of computational resources and access to very large data sets. In 2018, there was the ACM Turing Award, which we can qualify as the Nobel Prize for computer science, which this is not given by the Nobel Foundation, but that was, I would say, the similar role in terms of what it means to Yeshua Benjo from Montreal, Jeff Hinton from Toronto, and Jan Lecker from New York for their pioneer work on deep learning. So that was really confirming that this is really an important advancement in computing. And we saw recently, between 2022, the emerging of large generative models, both for text, for example, ChatGPT, that is very impressive in its capacity to interact and have some production of text, generation of text that is really impressive and good quality, and also images, things like DALL-E, Midjourney, which are able to generate high quality images from only one sentence or a few sentences. So these are, I would say, the kind of timeline that we see about, we know now about the neural networks. Then the question is, why now? Why it emerged at the end of the between 2005 and 2010? The conditions that allow that. First, it was the point that now we are in a situation where we have access to very large data sets. We are in an era of big data, thanks to the social networks, thanks to the web. The amount of data that is available has increased by order of magnitudes over the last 30 years. But now we are really in a situation where we have enough data to support training of big models. So that is an important condition that was required to achieve such advancements. We also see the availability of massive computing capacity, more specifically the capacity to use GPUs, which are first designed to support gaming, for example, or infography. So the point is that these devices that was first proposed for graphics are in fact making the same kind of mathematical operations that we need for training and using deep neural networks. So this is basically linear algebra with matrices, vectors, tensors. So this capacity of in terms of computation is significant, and being able to exploit properly a GPU on a standard PC workstation, for example, provide a capacity of computing that is comparable to a small cluster. So if we have access, and now we see the access of big computation clusters based on GPUs. So this is really important. It's really provide the compute power that was required to train deep networks on very large data sets. And the third condition is that we saw the emergence of new flexible learning models with priors that allow to deal better with the curse of dimensionality. An example of that is with convolutional neural networks. These are neural networks that has been proposed to deal with images first, and they are quite fit for that. So if we are dealing with images using only like pixels, values as input variables as is, without any kind of things, we will be we will suffer from the curse of dimensionality. There will be so many variables, and they are not processed in a way to take advantage of their structure, which is in fact or their lack of structure, in the sense that individual pixel doesn't mean much. What we need to look at is like many pixels in an area means something, represents often some objects or some parts of objects. So the capacity of having these new models that are flexible, but with the right priors regarding what we are looking, what we are doing, which kind of data we are dealing with, was also an important condition. So all these three together really lead to the capacity of training deep networks. For instance, multi-layer perceptrons, but with more than 2 hidden layers, with possibly many layers, tens of layers, for example. That was possible thanks to that. In fact, what we are one of the main motivation of deep networks is the capacity to learn a representation from and for weakly structured data. The point is that weakly structured data is the kind of data that we can find in a great amount, but that represents some more raw content, where the useful information is not clearly identified. Think about images, think about text documents, things about voices. These are type of data that is not directly usable, says with a SVM or a simple multi-layer perceptron with 2 layers, the thing that we saw before. So to be able to deal with that, this is opposed, in fact, to tabular data, where each variable is clearly identified. So if we say we are able to extract 25 different variables, and each of these variables we think it would be useful for the classification task at end, then we can just use, for example, an SVM on that, and that will work well. So we don't necessarily need deep neural networks to deal with such tabular data, but if we need to deal with images, usual approaches will not work really well. Because with a deep learning, we are looking often to extract some kind of representation from the raw data. And this representation should be and is adapted to the task at end. So we don't necessarily need to get an expert that will engineer the data in a way that is, we think, meaningful for the task. And we know this kind of domain expert is really expensive and not necessarily available easily. And often we just don't have expert on the field, or we don't have expert that is able to design a representation that is very effective. So with deep learning, we aim at learning automatically such representation to be able to deal with the raw data and define what we need automatically from the data to have a good representation that can be used for decision making. However, for learning such a representation, we really need a large amount of data at first to start with, because we cannot learn such a representation from only a few dozens of samples, because this is not representative enough. This is not rich enough to cover the different type of data with different variations of the data we can encounter for such an application. And for achieving, so the idea of making deep neural networks is also that we need to compose, to make use of model compositionality, which arguably is required in machine learning. Think about language. Language is in fact expressing really complex ideas. But if we are looking at written text, a written text is basically letters, and we don't have that many letters, 26 letters plus numbers plus some extra symbols, which are composed to build syllabs, which are making some sounds, which are making some words, and the words are used to build sentences, and sentences are used to make documents. And as such, we can express really complex ideas in documents, but basically this is a composition of letters, words, sentences, documents. And this allows to go from really simple basic items to really more complex ideas, complex notions. And as such, being able to exploit compositionality allows, I would say, an exponential gain in representation power, in the sense that, you know, if we are able to identify the right building blocks in our representation, we can arrange them in many ways, and all these different ways would mean something different. And as such, you know, having the right building blocks allow us to express complex ideas, and we can, I would say, have different level of such composition. You know, we can really go with simple notions that allow to build some more complex, still intermediary notions, which allow to build even more complex notions, which allow to express really complex ideas by composing them in some ways to express an idea. This is how language is working, and this is what the kind of thing we want to achieve with deep learning, to compose such things, to learn some elements that are organized together, to be able to provide, to have an appropriate description of the word, appropriate description of some data, to make a decision, says to classify an image. So in deep architectures, we have several layers of representation learning. And so we are kind of stacking this and going from low level to high level. This is how we explain that. It's not necessarily exactly how it works, because the learning is done automatically, but we see that it's kind of, it is well aligned with this idea, the way it works in practice. So model composition is useful to describe our world effectively. For instance, you know, we have here the idea that what we saw before, k-nearest neighbor classification, is an example of a local representation. You know, with k-nearest neighbors, what we see here on the left side, it is a representation of the nearest neighbor rule, where we have a Voronoi tessellation, where each cell corresponds to the region where a data will be associated to the prototype, or the data, which is the blue dot here. So this allows to kind of cut the space in different regions and do some processing. And so it works reasonably well, especially in low dimensions. But when we go in high dimensionality, and when we want to express relatively complex ideas that are composed with many things, it is quite limited. You know, we always need an instance to represent a new concept. So every concept needs to be enumerated explicitly through the training data that we use for, say, k-nearest neighbor classification. While if we are using some what we call distributed representation, so the idea is to have, for example, many linear hyperplanes. Like here we have 3 of them, H1, H2, H3. So the black, the blue, and the red linear discriminant decision frontiers. And the point is that we see that with these 3 linear discriminants, we are able to generate 1, 2, 3, 4, 5, 6, 7 different regions. So we are cutting the space with 3 hyperplanes. We have 7 regions. If we increase the number of discriminants here, it will grow exponentially. So we will get even more, because we are able to cut into the full space. So every time we have a linear discriminant, we can say that we are adding a power 2 to the number of zones that we are able to extract, well, more or less. So that is much more powerful than having some local representation. And each of these discriminants can be about a simple concept, but you know, we are looking at the composition of concept. Like here we are, like here we have the concept 1 is true, concept 2 is false, concept 3 is true. So we have this kind of 1 and 3 true, 2 false. So this means something. This means the composition of 1 and 3 minus 2. And as such, what we saw is that deep networks, when they are well trained, they are much better to learn than what we call fat networks. Fat networks are, in fact, networks that are not really deep, maybe with 2, 3 hidden layers, but with many neurons on each layer. So they are quite large compared to deep networks that should be more deep. So what we know is that the network capacity grows linearly with the width of a layer. So if we add more neurons on a layer, we will make it grow linearly in terms of capacity, but exponentially in terms of depth. So adding more layers would it says if we have the choice of doubling the number of neurons, if we keep the same number of layers and just doubling the number of neurons on each layers, the capacity of such network, which will be doubled, more or less, compared to a deep networks. If we are, in fact, we're doubling the number of layers in that network, it's more than doubling the capacity. It's much more. In fact, we will increase the capacity of the network to learn something. And what we see, in fact, it's more than that. It's not just that we are a more capable network, it's that such network, when properly trained, is learning well, is learning to do things better, and is less, appears to be in practice, not that much overfitting. It's not because it is more capable that it will be, I would say, prone to overfit very much. An example here is that we have 3 types of networks. So we have in blue CNN and convolutional neural networks of 3 layers. So we see that it is able to gain some capacity with a peak performance close to 20 million parameters, but then it starts to overfit and the performance is degrading. So it is an example of a fat network compared to 11 layers CNN. So basically with the same number, the same scale in terms of the number of parameters, it performs much better. So we go from 92% to 95% with the same number of parameters, but with a much deeper CNN. And what we see is that it still is not overfitting. We can go up to 60 million parameters, and it seems to be improving compared to 20 million. And we guess that maybe it will start to overfit in that zone here on the right. With much more parameters, but so far it seems to be, in fact, only improving in terms of accuracy, in terms of generalization, in fact. And we compare that to the green one, which is basically a multi-layer perceptron, fully connected layers. So we see that it doesn't have the right bias here, and it works with a comparable level to CNN, but with much more parameters here. Maybe about 35 million or so here. And if we increase the size of that network, it decreases in terms of performance. So there is some overfit here, which is, I would say, comparable with the CNN. It's just that maybe we need more parameters with the multi-layer perceptron to perform well in that specific case.